Okay. So now what we're going to do is we're going to put an RLC circuit together. All right. And keeping in mind, so this is my RLC in series. Okay. Of course, they can be done in parallel. I'll explain this a little bit after we're done here. Okay. So what happens is the following: is that the resistance, if I have a current I, so here I'm going to have I equal I max. Okay, so basically I'm gonna have so I'm gonna have an RLC circuit with a current source. A current source, it means that my I equal to I max sine of omega t, and the question, so my phi I is equal to 0, and the question is what is the potential around my battery? Okay, so delta V of the battery. Since they are in series, then delta V of the battery is equal to delta VR plus delta VL plus delta VC. Since delta VR gives you 0 phase, delta VL gives you plus pi over 2 phase, and delta VC gives you minus pi over 2 phase, then this problem cannot be solved by simply adding the potential differences together. And we will have to use the phasor diagram. Exactly the same thing that we did before. Okay, so this is depicted here. This is my current I. You can see that it starts at 0, so my phase is equal to 0, and then it increases, decreases as function. Now delta VR, it follows exactly the current because the phase is equal to 0. Delta VL leads I by 90 degrees, so it has plus 90 degrees. So it starts by this here, and then it goes down. And then the delta VC lags I by 90 degrees, so it starts at the bottom and then goes up. And so I'm going to have a sum of 3 sine waves, all right? Each has its own phase, and at the end, you know, I must have only one phase between the potential differences. And so the way to continue with this problem is by actually not, so basically, when you have this type of problems, always think phasor diagram, okay? Always. So this is the problem, is that because of the various phases differences that the 3 components have, the voltage just they cannot be simply added, and it has to be calculated via the phasor diagram. Okay, so let's go to phasor diagram. The current, what we said, the current is equal to I max sine of omega, right? Let's try to draw this phasor diagram. This phasor diagram can be drawn at any time t. But just to make it as simple as possible, let's put t equal to 0. Okay? If we put t equal to 0, what's the angle of the current is equal to 0? Because the phase is equal to 0 and t equal to 0. So omega t plus phi equal to 0. And so the current will have this direction here, which I'm going to redraw. Okay, this is my current direction. Okay. So that's my current direction. Okay. Now let's see what happened to the potential differences. All right. Well, the resistance does not add any phase. So delta VR, which is equal to R IR, this is, whatever was said here is set at max. Okay. Let me just add this here, just to make sure that I not. Okay. So max or RMS. So I'm going to have delta VL max equal to I max, and delta VR max equal to RI max. So everything here is in max, or as I said, in RMS value is the same. Okay, because what we are drawing, the vector, the amplitude is equal to the amplitude of the wave, okay, not to the instantaneous value. So delta VR max is equal to RI max. It has 0 phase. That's why my vector is basically parallel to I. Okay, I'm going to say this is my I max. Okay, that's the green. All right. Now, what happened to the capacitor? What we said last time, we just did it. delta VC gives me minus pi over 2 phase difference. So delta VC max is in this direction. Okay, is in this direction. And let's do it by some, let's say by red, yes, red. Let's give it more. So that's my delta VC. Okay. So the amplitude is delta VC max equal to I max multiplied by XC, capital XC. I remind you that capital XC is the same thing as capital ZC is equal to 1 over omega C. Now, what happened to my inductor? My inductor add plus pi over 2, okay, with respect to the voltage with respect to the current. Okay, so I'm gonna go back here and I'm gonna draw this. That's gonna be my okay. So what do we have? We have delta VL, which is going to give me plus pi over 2, and delta VC will give me minus pi over 2. Consequently, and this is at any time t, not only at t equal to 0. This is always, yeah, as I said last time, is that the capacitor always give a plus pi over 2 phase difference, and the inductors always give minus pi over 2 phase difference. But it's also, you have to be careful what is given and what is requested, okay? Here, what's given is the current, and what is requested is the potential difference. So delta VL and delta VC are collinear, so basically they lie on the same support, okay? And I can very easily calculate delta VLC, which is equal to delta VL minus delta VC. And the arrows, I repeat, indicate they are as vectors. So I can calculate delta VLC is equal to delta VL minus delta VC. Once I do that, then I'm gonna have then this phasor diagram, okay? This phasor diagram turn into a delta VLC. So basically, I'm gonna subtract these two, and if I subtract these two, I'm gonna have delta VL minus delta VC. So this is one arrow like this, and this is delta VR here, and thus delta V around the power supply is gonna be this one here, delta V. So once again, I'm going to use Pythagore. That is delta Vx square equal delta Vr square plus delta VLC square, which just means delta VL minus delta VC, the whole thing squared. Okay. I replace delta VR by I max R, delta VL by ZL or XL I max, and delta VC by XL XC I max, and then I'm going to have delta V max equal to ZF multiplied by I, where this impedance or reactance is equal to R squared plus XL minus XC squared. Furthermore, I can calculate the phase phi as tangent of phi equal delta VL minus delta VC, this value here, minus divided by delta V R, which is this value here. And so once again, I have a delta V max, which is the amplitude, equal to I max ZF. Sorry, there should be a max here. Okay, so this is going to be max. This is going to be max. I'm sorry about that. It's going to be max, but I hope that you get the point. Is that what we're talking about this here is the amplitude of the wave and not the instantaneous value. Okay? Let me put this also here. Delta V max and delta VC. Okay, so the final result is that I have the impedance of my circuit, Z total equal to the square root of R squared plus parenthesis XL minus XC squared, and I'm going to have the phase, which is XL minus XC. But now, so basically, now what we're going to try to do is, okay, so again, you know, what happened here is that we made omega tends to 0, omega tends to infinity, and as omega tends to 0, okay, then the capacitor acts as a open circuit, and then the current is equal to 0. And this is going to be the same here. So if omega tends to 0, excuse me, if omega tends to 0, then this capacitance will cut the current, and the current will be equal to 0. Okay? So let's try to study this reactance of the circuit, or this reactance of the circuit, as a function, of course, of omega. R, L, and C are usually fixed, and what changes is only omega. Okay, I'll come back to that. All right. So once again, if I'm talking about maximum RMS value, is the same thing. All right. There's only a square root of 2 between them. So what happened now? My IRMS or my Imax is equal to delta V RMS or delta V max divided by this capital Z. Right. All right. So let's see what happened at different values of omega. When omega tends to 0 or F tends to 0, this guy tends to 0, right? 1 over omega C tends to infinity. VRMS divided by infinity, this gives me Imax tends to 0. Okay? So, let me see if this is somewhere discussed here. So, let me do it here. Just in case, we'll see. Okay, so we are studying here. Okay, this is what. So what we said is that omega tends to 0 as a first. Let's try to see what happens when omega tends to 0. Okay, when omega tends to 0, we have XL tends to 0. Right? لأنه XL, which is equal to omega L, okay, tends to 0. Now, sorry. Now, how about ZC? In this case, when omega tends to 0, I have XL tends to 0, and I'm going to have ZL tends to infinity, right? ZL is 1 over omega C, all right? If ZL tends to infinity, this means that my Z effective tends to infinity. If my Z effective tends to infinity for a given delta RMS, this means that my Imax tends to 0. Right? Okay. Now let's take a look here. So this is my impedance, the blue curve, okay? And the red curve is the current. So what you see is that when omega tends to 0, okay, the left-hand side here, all right? When omega tends to 0, then Z tends to infinity, and my I tends to infinity. So when omega tends to 0, the capacitance is the key player, because what you saw here is that what's going to tend to infinity is basically the capacitor. Okay, so this is Z, should be ZC. Okay, the ZC tends to infinity, and this is ZF tends to infinity, and that's I by Z. Okay, I hope that this is clear. So this is X L. Okay. Okay. Now, what happens when omega tends to infinity? Okay. Well, XL is equal to L omega. So if omega tends to infinity, then your XL tends to infinity as well. What happens? Sorry, I'm using X's and so I'm going to call capital Z. So okay, so this is capital Z. But Please remember that capital Z and capital X are used as inductive, as reactants. Okay, so my ZL tends to infinity. Okay, fine. What happened to ZC? My ZC is equal to, remind you, 1 over is equal to 1 over omega C, right? And thus, if omega tends to infinity, 1 over omega C tends to 0. So that's this ZC tends to 0. Remember, and what we said is that at omega tends to infinity, the signal oscillates so fast that the capacitor does not either charge or discharge. Okay, consequently, it does not have any role, and that's my ZC tends to 0. Okay, now let's see what happened to the total Z. Okay, well, the total Z. This is the total Z. Sorry. Okay. What happened is the following. So this terms tends to 0, was 1 over omega C, when omega tends to infinity. And this terms tend to infinity. So my ZF also tends to infinity. If my ZF tends to infinity, then my Imax or my RMS tends to 0. Consequently, if I go back to this graph here, okay, wait a second. Okay, yeah. If I go to this graph, when F tends to infinity, okay, to the right, then my Z effective, my Z, the impedance of my circuit tends to infinity, okay, and my current tends to 0. So what happened in this case, what you can see is that the guy who's playing the role is basically the inductance in this case. So what happened? Remember, the inductance plays the role of a battery, right? And plays the role of a battery only when I have time variation. So when I have time variation, when my time variation is very fast, this means that my omega is very high, okay? Then this inductor will generate a battery. Remember, inductor plays a role as a battery. It generates a battery equal and opposite to the real battery, okay? Because if you recall also, what we said is that according to Lenz's law, then this battery will come to oppose the change. So if this guy is increasing, this is going to come to decrease it. But since omega tends to infinity, then this opposition is optimum, and thus I have a virtual battery equal and opposite to the real battery. And this is all the time, since the signal is always oscillating up and down. Okay, so I go back here. So here, if I go back here on this side, the capacitance, the capacitor blocks the current as it is fully charged. Okay, so this is on this side of what's happening. And so this is, let's say here, this is blue. Okay, and now if I go on the other side, here, what happened is that, let's put it in green. In this case, what happened is that the inductor generates an equal and opposite electromotive force, okay, which leads to a current equal to 0. As if I have a battery, but at the same time I have an equal and opposite battery. Okay. So here the inductor plays the role, and here the capacitors block the role, block what happened. Okay. Generates an equal and opposite since the the current is, or the voltage is oscillating as a function of time. Okay? So, but this leads us to a value for which my current is maximum. Okay? My current is maximum correspond to an impedance which is minimum, right? So this is what this F0 stands for, all right? And so this F0 is called resonance frequency, all right? And it's going to be equal to 1/2 pi square root of LC. And why is that? If I take a look at, again, at this value here, okay? And if I take a look at this value here, if XL is greater than XC or smaller than XC, it doesn't matter. Because why? Because I have XL minus XE squared. So I will always have a positive number added to the resistance. So my ZC, the minimum value it can have is actually equal to R. And this is where this term, okay, is exactly equal to this term is exactly equal to this term. When this term is equal to this term, then this is equal to basically to 0. This term here is exactly equal to 0. Yeah, we're done. This term is exactly equal to 0, and so my Z is equal to R. So this, when you put 2 pi F0L equal to 1/2 pi F0C, then you end up having this value, F0 is equal to 1/2 pi square root of LC, and this is your resonance frequency. So at this resonance frequency, you have maximum current and minimum impedance in your circuit. Okay? So I consider this is done now. I'm gonna